In this video, I want to go over the solution to the Bayesian problem that was assigned. And in the solution, it's very similar to the illustration that I used to present Bayesian theorem. Bayesian theorem really comes back to conditional probability. And you can follow along in the statement that you were given. You were given that a senator is campaigning for re-election and is trying to raise $100,000 for a last-minute series of television advertisement. He thinks there's a 55% probability that he will be able to raise the money, and that if he does, there's an 80% chance to be re-elected. So when we look at these types of problems, in other words, when we're trying to do, and I have found the easiest way to present the Bayesian theorem is to always think in terms of a tree diagram. So right off the bat, we know one thing. We know that this particular senator thinks there's a 55% probability of raising the money. So therefore, if there's a 55% probability of raising money, there is a 45% probability of not raising the money. Money, 55, complement of money is no money. So that's what we know. So when you look at these types of problems, it's always good to extract from, in this situation, the word problem, what you need. And then it goes on, 55% are raising money. Then it goes on and he states there is an 70% chance to be re-elected. So right up here, the tree, we can just put, re-elected, there's a 70% chance. Complement, once again we're saying 55% chance of raising money. If we raise the money, there's a 70% chance of being re-elected. And the complement of being re-elected, of course, is non-elective, and that's 30%. And so it goes on, and it says down here, right, no money is 45%. He also feels that if he fails to raise the money, right down here, then there will still be a 55% chance of being re-elected. Okay, this is an outcome. No money raised, 45%, and of that, he still has a chance of being reelected at 55%. The complement of that would be non-elected at 45%. Raise no money, well, don't raise the $100,000, 45%, and of that, there's a 45% probability that he will not be elected. So this is what I'm saying from the standpoint of always doing a tree diagram. Yes, it's more involved, it takes longer, but with a tree diagram you are going to know immediately what the various outcomes happen to be. And so when we look at that, let me just kind of scroll up here. So what we have, let me come back down here. What we have is that one possible outcome is that the money is raised and he is re-elected. What's the probability of that? 38.5%. Raise the money, not elected, is 16.5%. No money, re-elected, is 24.75%, and no money and not being elected is 20.25%. And of course the sum, and these are all possible outcomes. Let me point that out. From the tree diagram, we can isolate on all possible outcomes. Money, re-elected, money, not re-elected, no money, re-elected, no money, not being elected. So therefore, these are the only possible outcomes, probabilities, and they must sum to 1. Now in this particular case, the question stated that given that he was re-elected, if you recall when we kind of first went over probability, simple and joint probabilities, under conditional probability, I stated that when you know something, that's going to be very critical, and that's going to be very, very important. So what we have here, we know something already. Given that he was reelected, what we want to now determine is what's the probability that he did not raise the money. Did not raise the money. So let me scroll back up here. And so what we have here, money and reelected, right, was that 0.385. Money and not reelected, 0.165. And all what I'm doing now is simply digressing and going over all possible outcomes and assigning the probabilities to those outcomes. No money reelected, no money and not being elected. 4 possible outcomes, those outcomes equal, of course, 1. And then what I have stated here, given that he was reelected, what is the probability that he did not raise money? That he did not raise money. Okay, that he did not raise money. So let's look at this denominator first. Given that he was reelected. Oh, he was reelected. There's a possibility that he was reelected here. Reelected and money, right? 0.385. And there's a possibility that he was reelected and not being able to raise the money of 2.475. So given that he was reelected, right? He could be reelected, raising the money, not raising the money. That's in our denominator. In the numerator, given that he was reelected, the probability of not raising money, reelected and not raising money, was 0.2475. Therefore, given that he was reelected, what's the probability he did not raise money? Is 39.13%. So I don't want to spend a lot of time on the Bayesian theorem. My point here is that when you have a word problem that deals with conditional probability, the first thing that you should do is simply establish a tree diagram, as we did here, from the standpoint of isolating on the identification of all possible outcomes. You were given 55% of raising money. You knew the complement had to be 45. Then you were looking at being reelected with the money. That was 0.7. You know its complement is 0.3. The point is, yes, it's a little bit longer to do, but from this particular case, you are able to identify all possible outcomes, and you're able to identify the probabilities for all possible outcomes. And saying that, then you should be able to determine whatever the probability happens to be for any of the outcomes, i.e., probability of money and reelected, probability of money and not being reelected. You have that. In this particular case, you know something, and this is how we went about finding that particular solution. So once again, as I said, I'm not going to spend a lot of time on Bayesian theorem. My point once again is that when you have this type of a problem, focus in on the tree diagram, i.e. from the standpoint of looking and being able to determine all possible outcomes and the probabilities to those outcomes in order to come up with a solution or the answer to whatever any of the probabilities may be.